So the price has gone down dramatically over the years, and the install capacity has increased obviously exponentially, and we can only see continued growth of lithium-ion batteries because there are a lot of applications that are hinged on a successful development of lithium-ion batteries. The price has gone down, but it looks like it's quite stabilized, although sometimes we still see noises of like, $50 per kilowatt hour, or even some of the numbers that we have seen recently could be even lower than that. But for the high-end product, the price is quite stabilized now. But obviously for the future development, if we can get down the price even further, that would be great. So there are a lot of motivations for us to work on specifically on cathode materials. My talk is focusing on cathode materials. This is not discouraging anyone, either in my group or in other people's research group, discourage them from doing any other type of research. I think every single component in the batteries, is important. The rationale behind us on the cathode, when I first established my independent research program, is that I want to have a chemistry that could work for all type of batteries. So no matter whether you work on liquid state, solid state, semi-solid state, or solid state, you name it, there could be 10,000 different ways to name your battery chemistry. There are also, all solid state batteries. There are a lot of different ways of naming it, but you do need to have a functional high performance cathode to go with it. If you break down the cost of cathode, the cathode materials could be easily roughly around 50% of the battery cell cost. So there's a lot of driving force behind that from the cost standpoint. And the other thing that looking at the cathode materials development and cathode research in the United States, we have to look into this map. This is a map generated by some of my students. Their photos will be seen later. This is really an analysis of the global, specifically in the market of electric vehicles. As I said, there'll be a lot more applications for lithium ion, but this presentation, we have most data for electric vehicles. So if you look at this, EV adopting countries are labeled as sort of a blue color, and we define that as over 5% adoption in the market. And you can see that ours here in the United States and Canada and west part of the Europe, they are the EV adopting countries. But we also have seen countries that are both EV adopting and materials extraction. For example, China and Australia, they are both producing materials performing materials extraction. And then they're also, especially China, manufacturers probably close to 70 to 80, or even higher than that today, lithium-ion battery manufacturing. But then you also look at other countries that are labeled as sort of yellow-green color. Those are mostly materials extracting countries. So you can see there's a distribution of different roles in this entire battery supply chain. One interesting country we found is Japan. Japan produces a lot of batteries, but they are not an EV adopting country. So that's a very interesting phenomena. But obviously, they are not the materials extracting country either. For us in the United States, we get some unique challenges. There's critical gap simply because there is no U.S. cathode supply chain. This is a slide made by CEO of Fermi Energy, Ray Xu. He has been looking into commercialize some of the technologies that we develop in the lab, and he did some analysis. The U.S. produces less than 0.25% of the global cathode active materials, and obviously there are a lot of applications in the space, defense, that really need to have batteries and battery cathode materials. So that's a very unique challenge that we face here in the US. But if you look at the complexity of the entire batteries supply chain, and obviously I was going to give a lot more discussion on all of these paradoxes, but then as I was preparing for this presentation, I decided to switch a little bit away from talking too much about policy, talk too much about environmental aspect of the battery manufacturing, to mostly focus on the technical aspect. But this is an overview of what we think about the complexity of the battery supply chain. And so we can often overlook a lot of things that we think that a policy that will promote the use of batteries or electric vehicles could lead to a reduction in the carbon dioxide emission. But oftentimes that's not as simple as that. Oftentimes when you get a policy in place, they could even temporarily increase the emission due to the concern over the future that we will not be able to do fossil fuel extraction. So you can increase the carbon emission temporarily. But certainly there are also other things, raw materials extraction that lead to battery manufacturing and electric vehicle manufacturing. And the fuel cycle is another very important aspect. So if you look at the vehicle use, if you drive an electric vehicle, you get to charge your electric vehicle, and then where do you get the electricity from? Really, what determine how clean your electric vehicle is going to be. So it's not a simple solution saying that you get electric vehicles, you will reduce the carbon emission by a certain percentage. The number is not fixed. It's really depending on where you are and how you charge and where your electricity is coming from. There has been a lot of discussion over the end of life vehicle use. Obviously you can use, people thinking about using electric vehicle batteries as a second life batteries for other purposes, such as storage purpose, that could potentially have different or lower requirements compared to electric vehicle batteries. But for the most part, that's still a assumption that other applications will have lower requirement than electric vehicle batteries. But towards the end, we need to get them recycled and then go back to the raw materials processing, refining, and then battery manufacturing. So you want to form this loop as enclosed as possible so that it can be as circular as possible. Now, later in my presentation, I will be mostly focusing on just the cathode materials. And I want to specifically emphasize on something we call energy efficient manufacturing, or you can consider that as low carbon manufacturing, because energy efficiency is usually related to the carbon emission during the manufacturing. So then if we get energy efficient manufacturing from the manufacturer's standpoint, that can get them technology advantage, that could also increase their profit margin because the energy contribution to the manufacturing is a substantial component of the entire profit margin model. So this scheme was created by these three students and postdocs, and they are working on a very interesting perspective to discuss the paradoxes of all these different factors in the battery manufacturing supply chain. So there are another level of complexity we have to recognize. This is also a scheme that we summarize for the relationship between the policies in different countries and also the global policy on the bottommost. We have this global policy, for example, Kyoto Protocol, Paris Agreement. They all had very aggressive targets in terms of cutting emission or in other kind of environmental aspect. On the y-axis, there are different countries. They also have their individual policies related to this carbon dioxide emission. But then if you look at the atmosphere, carbon dioxide level is just keep on rising over the years, and it's actually increasing after the rate of increasing. The rate of increase has increased dramatically also after the beginning of the new century. So there isn't direct correlation between how we place the policy and how much carbon dioxide emission we can decrease. So there are a lot of complexity going into this. It's not just the policy could play a role, but there are other factors that we have to take into consideration. For example, population, the need of improving everybody's life, and those kind of factors are important. And oftentimes are more important, more determining than a lot of these policy factors. Of course, we doesn't mean that we shouldn't have policy. We should always have policy to encourage people to do the things, but we also need to work on something else. So as individual material scientists, I'm thinking, you know, can we at least do some fundamental studies to improve the way we make the materials? So coming back to the energy use and vehicle, energy, electricity sources and vehicle emissions, I put out get a data from, this is in the Department of Energy's Alternative Fuels Data Center. You can search this, you can get all this information online from the Department of Energy website. So this is the state of Georgia. This is where you guys are situated. So if you look at the electricity sources, you get a lot of nuclear. Looks like you get, this is the data from 2023. You get about 30% nuclear energy. That's very good percentage of nuclear energy already installed in your state. Natural gas is obviously the biggest pie, and natural gas being the biggest pie is true for a lot of states. It's about 47%. Solar has also pretty good presence, and coal is still has 13%. So depending on, well, if you drive different type of vehicles in your state, and then the annual emission per vehicle. If you drive your gasoline car, this will be the annual emission of your carbon dioxide equivalent. And then if you're driving all electric, and with the electricity coming from this kind of electricity mix, you will emit about 2.5 pounds of carbon dioxide. So you get, even with this kind of electricity mix, you get a lot of benefit from going to electric vehicles. Now let's look at another state, Rhode Island. This is where I am right now. Rhode Island has predominantly natural gas. This is 86% natural gas. Recently, I bought a house, and the heating obviously is a natural gas. There are a lot of use of natural gas in our neighborhood and in the state. So 86%. And then if you go for electric, compared to the gasoline, you also get, substantial reduction of the emission coming from the vehicle use. Now let's look at the third state. This is California. California obviously has a lot of more solar, I believe, and then also geothermal has a big contribution there. Nuclear has reasonable contribution. Hydropower has contribution, and then you get this. The emission from the driving the electric vehicle will be lower than the previous two states, as you can see there. So you get more benefit by driving electric vehicles if you're concerned about the carbon dioxide emission. I encourage everybody to go into this Department of Energy website to search for all different type of data. They have a lot of data that you can extract for your presentations. I found some of these data are very useful to illustrate how different type of electricity mix could lead to different emission. So if you drive the same electric vehicle, you don't necessarily contribute to the carbon dioxide emission the same way as you are in different countries or different states. And this is another way to look at it. There's a, in terms of the battery manufacturing, you get carbon dioxide emission for the vehicles. But in the use case, depending on what kind of electricity mix, you get a huge error bar in terms of the fuel cycle. That's another illustration of the three states that I discussed in the earlier part of the presentation. All right, so speaking of the cathode chemistry, there are predominantly different type of crystal structure. One is olivine type of crystal structure, lithium iron phosphate. It's a very popular cathode materials for electric vehicles, and predominantly due to the safety reasons, and cost is another reason, being free of nickel and cobalt. You can see that there isn't much raw materials cost concern. but because of the phosphate PO4, it also stabilizes the structure and will have no oxygen release compared to other type of cathodes. For example, these two types of oxide cathodes. This is a spinel cathode. This is a layer cathode. For the most part, we can talk these two different type of cathodes today. There's the reasons why we would choose different type of cathode for different type of use. They give different capacity. As you can see here on the x-axis, depending on what type of cathode you have, you get different capacity. They also give you different voltage profile, which obviously capacity and voltage these two will determine the power density and energy density of your batteries. And the anode is also important, but the cathode is really the limiting factor in terms of the energy and power. So over the years, we look at cathode chemistry in my group all the way from molecular level understanding, chemical bonding understanding, to all the way to component design and building pouch cells. So we're looking into almost across the entire length scale. And a lot of those studies back in the day were looking at, for example, fading mechanisms of different type of cathode materials in different type of use environments. For example, when you get cathodes or when you get batteries perform at extreme low temperature or extreme fast charging, you would not expect them to have the same degradation mechanism as at room temperature or as at elevated temperature. So the degradation process and kinetics are very much related to how you use your battery materials. So we have a lot of studies in that area. There's another thing that we start to think over the years is the manufacturing process of, for example, nickel-rich cathodes. So most of the studies that are presented in this slide here, they're based on the layer cathodes. So layer cathodes, they are nickel manganese cobalt base. There's a overwhelming trend over the last few years going for nickel-rich layer cathodes. Obviously, the trend is going back and forth, right? It's 5 years ago, or maybe 6, 7 years ago, everybody was talking about nickel-rich layer cathodes to get a high energy density for electric vehicles. Now these days, people start to talk about lithium iron phosphates, lithium manganese iron phosphates, and there has been a lot of different type of predictions over what type of chemistry is going to be dominating. So I have a prediction here. This is from reference, but I encourage you not to take this kind of prediction very seriously. It's because the prediction can change dramatically. No one can really predict what the market direction will be in the next 2 or 3 years. So in this prediction, based on this prediction, we are seeing increased use of nickel-rich layer cathodes. So you can think of this as if really the market is driving towards the direction of high energy density, nickel-rich NMCs is probably going to play a very important role, because nickel-rich can provide much higher energy density than lithium iron phosphates and other low nickel version of the cathodes. So if we believe in that assumption, then we get to think about how this type of materials are being made. So in order to lithiate the materials in the initial manufacturing, we need to have a lithiating agent. So lithium, basically, you can use lithium hydroxide. You can also use lithium carbonate. Of course, there are other lithium salt people are thinking about, like lithium nitrate. Lithium nitrate is not a typically friendly chemical because after thermal processing generates nitric oxide. It turns out that lithium hydroxide is preferred for the calcination of NMC materials due to the low melting point and the crystal growth behavior of the NMCs when it's calcined and using lithium hydroxide as precursor. But obviously, lithium hydroxide also contributed to more emission, and that's because lithium hydroxide is predominantly sourced from ore, and the overall emission and energy use is they are higher than coming from, for example, other kind of sources. So we get going for nickel-rich or already have one penalty, that we use the use of lithium hydroxide. If we can use lithium carbonate, that would be great. We are also trying to find ways to use lithium carbonate. So how do we do this kind of studies? The first thing we do usually, we want to control grain growth. On the figures on the right, there are SEM images of different type of microstructures that we have studied over the years. But then the other thing is not just the morphological information. Morphological information will give us information such as tap density of the materials and the packing density that will be related to volumetric energy density. But we also want to understand how the phase transformation is happening. So to do this type of study, we would take the precursor material, which is usually metal hydroxide, such as nickel, manganese, nickel, manganese, cobalt hydroxide, and then we mixed with lithium hydroxide precursor and heat it up to different temperature and monitor the phase transformation behavior to investigate at what point layer phase starts to form, at what point we can finish the crystal growth to obtain the final product. So by doing all these diffraction studies, this can give us indications on how to control the temperature profile. And this is one example of that type of study. This has been a study for this study was published more than 5 years ago now. So microstructural control, you can get two different materials with identical composition, but they have different microstructure. This is really where material science can play an important role. Chemistry is mostly about chemical composition design, doping and coating and all those kind of process to improve materials. We found that if we use the material science principle, just by controlling the grain microstructure and the grain morphology, you can get the same chemical composition, they will behave totally different. And one example of different behavior in this chemistry is if you look at the charge distribution. So the way we did this was you can charge up the two different type of materials to the same state of charge, and then you go ahead and map the nickel oxidation state distribution inside individual particle. And then you will be able to figure out that which part of the particle gets oxidized, which part of the particle hasn't get oxidized. So it turns out that if you get the rod NMC, the charge domains are radially aligned, which has very similar microstructure as the grain microstructure that you're building. So this is experimental data to demonstrate that same chemical composition, you could get different type of state of charge distribution inside the individual particle. Now, if you are interested in mechanical behavior of battery particles, this will have huge impact on those properties, behaviors, because the charge distribution will impact how the strain is distributed inside the particle. So knowing all those kind of things, fundamental aspect of how different particle morphology, different microstructure can dictate the behavior of the cathode materials in the final performance. We have started looking into some additional factors, which is the production. So conventional cathode active materials production requires calcination, and this refers to mostly layer cathodes, 800 to 900 degrees C, usually for extensive number of hours. And the rough estimation, each 1 kilowatt hour of cathode active materials will consume 7 kilowatt hour of electricity for calcination. And that will contribute to the cost of making. That will decrease the profit margin for the manufacturers. So how do we do better calcination to get the temperature lower, right? So, but to think about this, we have to think of this from more philosophical standpoint. We have been using fire for many years. I don't know how many years. I was not there when the fire was invented or when the fire was started to being used. I was not there, but I can see that we rely on a lot of high temperature process, and it's almost like by default when you want to sinter ceramic or you want to get ceramic powder, you use high temperature process, and there's a lot of energy barriers throughout the entire thermal process. You can do that. You can imagine that as a scheme like this. If you want to go from here to somewhere else, like maybe here, you have to go through all these energy barriers. Or of course, you can find a way to navigate to go always through these low energy barriers and then climb up. So it's really about how to navigate the energy landscape that allows you to avoid some high energy barrier steps. And that's one unique aspect of battery cathode materials calcination is we have multiple factors that are in play. For example, in the typical sintering of ceramic, let's say aluminum oxide sintering, you don't get the oxidation state change. Aluminum stays as aluminum 3+, so it doesn't change oxidation state. But the calcination of battery cathode active materials involves a lot of oxidation state change. For example, in nickel-rich layer cathodes, you have to oxidize nickel from 2+ to somewhere close to 3+, and that needs a lot of oxygen. You also need to have high temperature to initiate the phase change from one phase to another and to the final phase. That really involves a lot of breaking and reorder of metal-oxygen bond and also restoring cation symmetry. So there are a lot of things going on during that entire thermal processing. So as I will show in the next few slides, my student Junyi Yao, he has been working on this for a couple of years. Now he is able to scale this up to kilogram scale for very low temperature making of the cathode materials, reduce temperature by a lot. And as I mentioned, the grain growth is important. The grain growth is also very sensitive to the temperature profile. So here is an example of two different type of grains. If you do that at 720 degrees C for 6 hours, you get radially aligned grains. If you get that to 780 degrees C for the same number of hours, you get randomly aligned grains. They have the same chemical composition and almost the same lithium content in the final active material, but 60 degrees C difference can already provide huge difference in terms of the microstructure. So this is another reason that we need to look into the temperature much more closely. So how does the synthesis happens during a normal process? So this is an X-ray diffraction contour map of the phase change during the calcination. So on the bottom here is on the left-hand side, here's the temperature axis. And you can see that we get diffraction peaks in the beginning. They are the precursor metal hydroxide peaks. And then as we go higher temperature, it gradually transforms into the layer phase. As from here, you can see the layer phase start to form at around 400, 500 degrees C, and then get more obvious as you go for high temperature, like 800 degrees C. So this is a phase step, further analysis of different phases that are present at different temperatures. So there's a layering that's happening above 550. You start to see this buildup of this 003 peak belonging to the layer phase. So if you look at the kinetics at low temperature following the traditional pathways, the traditional pathways being the pathway that people are taking, the calcination actually starts from the layers, metal hydroxide to a rock salt phase, and then to the layer phase eventually. The rock salt phase is very stable. It's not easy to convert to the layer phase because cation ordering will take a lot of energy. So let's look into the method that we could use. That, for example, we use a traditional method. And traditional method, we did kinetic studies at 600 degrees C and 625, 675, 700 degrees C. And we can monitor the kinetics of growth for different materials. So for example, here we get lithium nickel oxide calcined at 550 degrees C, which will be a temperature that's 200 degrees C lower than the traditional temperature, and the same thing here with 90% nickel, and here's with the 80% nickel. So after 1 week, we still get rock salt percentage as around 24% in the lithium nickel oxide case, and rock salt percentage increase as we have higher manganese and cobalt. So rock salt still remain at 47%. So that means if we use traditional methods, even after 1 week of making at this temperature, we are not able to convert to the layer phase totally. There's still a big fraction that's stuck in the rock salt phase. But we recently started to manipulate the reaction pathways for low temperature layer synthesis. I could not go into too much detail on that, but comparing the extra diffraction that you are seeing here versus the diffraction data that I've shown earlier, neutron diffraction, I believe, you start to see that phase change is much smoother and initiated at much lower temperature already. You start to see the layer phase formation. And here is the temperature at 250 degrees C for only 5 minutes. We start to see buildup of the layer phase. And the C to A ratio is 4.958. That's very close to a nice layer phase. So this is called layer intermediate phase. If you look into the final calcination at 550 C for 10 hours, now you get very beautiful layer phase, and which is 100 to 200 degrees C temperature decrease compared to the traditional process. And the cation mixing is only 3.4%. I didn't mention the crystal structure too much. Cation mixing means that lithium and nickel, they are mixing their sites. Ideally, you want to have lithium on the lithium side, nickel on the nickel side. You can allow potentially a few percentage of the cation mixing, which will be okay. And some people found that a few percentage actually is beneficial for the performance, but you cannot allow for having too much nickel and lithium cation mixing. So our cation mixing is very low, and they also perform extremely well in the long-term cycling. And we are now, because now we have the capability of doing kilogram scale, we are now making larger battery cells and delivering materials to our industry partners, American Lithium Energy and GM, for our validation. I think our first step is to deliver the materials to American Lithium Energy. They are a big supplier of batteries to the defense space, and we hope that we can get our materials validated by American Lithium Energy so that we can demonstrate the technology for this, for our low temperature calcination. And this project is at the moment funded by the MTO program at Department of Energy to achieve low cost effective layer cathode manufacturing. Remaining a few minutes, I want to highlight the other aspect of the importance, which is, I talk about nickel and cobalt containing cathodes, and the way we do it is to lower the temperature of making. And then the other factor we have to think about is domestically sourcing of raw materials. Nickel and cobalt are not readily available in the United States, and you can look at this distribution of different reserves in the globe. And then U.S. obviously has very tiny fraction of the current known nickel and cobalt mines. Reserve is extremely low. So Dawei Shah, he recently graduated. He started looking into manganese-rich cathodes. So he started with a spinel, which is a commercially available material. Spinel is a very good material for the fact that it contains only manganese, which can be domestically sourced very easily. Well, at least we have a lot of manganese minerals in the United States. Traditionally, if you use the spinel, the operating voltage is roughly around 3.6 to 4.2, 4.3 volt, and the specific energy at the materials level is around 400 watt-hour per kg. And one thing that he did was he takes the original lithium manganese oxide spinel commercially available, he mixed with carbon materials and perform a ball milling. Once he performed the ball milling, he was able to get the carbon coating on the surface of the spinel materials. There are also some structural transformation. And in the end, he was able to get the materials level specific energy up to 800 watt-hour per kg, which is higher than a lot of manganese-rich disordered rock salt cathodes my group is working on. And these are the manganese-rich disordered rock salt charging up to only 4.5, 4.6 volt. We were not going to high voltage, otherwise you can go even higher energy density. The process that he uses is really simple. Just take ball mill mechanical milling of the spinel with graphite materials, creating carbon coating on the surface. On top of the carbon coating, we actually found that we are creating disordered materials. So now we get spinel is a cubic structure, and then after we perform mechanical milling, we get somewhere between disordered spinel and disordered rock salt type of structure and locally. This is done through neutron diffraction. We can figure out the structural disorderly. So the sample is labeled as partially disordered. It's not totally disordered, it's partially disordered. And O here represents the original material. And by doing so, if you take the original material, you charge and discharge, this is your voltage profile, right? It has this capacity at the high voltage range, and then you get the capacity around 120 milliamp hour per gram. But if you perform the materials perform mechanical milling of the material and create this partially disordered spinel material, you get additional plateau that's present at around 3 volt. Is being activated. You get now higher capacity, and then you get higher energy output from that material. Obviously, it has a lot of other practical problems we have not solved yet. For example, there's a big jump of the voltage between the two steps. This is not a great thing. We need to solve that problem in the future. And from this CV test, you can also observe the two different redox process, high voltage redox process and low voltage redox process. This material can perform at very fast rate. So the energy retention at 4C is 93% compared to a 1C rate. This is charging at a high C rate and discharging at C over 3. We don't see a lot of energy penalty between the 1C and 4C. And the energy efficiency at 4C, this is the round trip energy efficiency, is 88%, which is higher than a lot of other disordered materials, such as disordered rock salt. So this is the rate performance. And we still have pretty high cathode active materials loading, 86%. Obviously, we want to increase this to 96%. We still get some conductivity problems with this material. Otherwise, we can go even much higher cathode active material. But you don't see a lot of rate penalty as you go for high C rate. The mass loading here is around 1.5 milliamp hour per centimeter square. And then long-term cycling showing encouraging result. This is a full cell. This is half cell on the left-hand side. We incorporate a localized high concentration electrolyte into our investigation. On the right-hand side, we have graphite full cell. They perform quite stable over 70 cycles. But I have to say that for longer term cycles, we still get some problems. The reason we use localized high concentration electrolyte is to mitigate a lot of issues with manganese-rich cathodes, such as manganese dissolution. The localized high concentration electrolyte can help us at least mitigate some of the dissolution problems. So this is our perspective on how we can simplify the materials making by taking existing commercial material, perform a mechanical milling to create disorder in the cathode, and meanwhile creating carbon coating to help with the conductivity. We still have a long way to go, but I think this elemental simplicity without going for complicated doping, without go for a complicated synthetic process, just through a dry mixing step, using mechanical milling could be a great pathway for the cathode making. And manganese obviously is much lower cost and much more available compared to nickel and cobalt. We have a lot of thinkings in this direction, going for manganese and iron and other type of earth abundant elements, and in not just lithium ion battery research, but also in sodium ion research. This is the take-home message. Batteries are very important, and I only touch on some applications, some aspects of lithium-ion batteries. There are a lot of other battery chemistry, but that we should also recognize there are a lot of paradoxes in the environmental, economic policy, social domains. But for us, we believe that there's a great need for us to have improved manufacturing so that we can align our manufacturing technology better with the environmental and economic goals. So one number I didn't mention, I would mention here, the profit margin for cathode active materials usually in the single digit percentage, 5 to 10% range of the profit margin when the manufacturers are making these materials and sell them. Now, if you think, okay, we reduce the electricity use, reduce the energy use during the manufacturing, that can save us 5% in the cost. If you just take the 5% in the cost, it doesn't give you a big number, it's just 5%. But if you consider that profit margin is only 5%, you add that up, you actually potentially double the profit margin. So that will give you a lot of technology advantages. And a lot of these understandings after over years of studies, leveraging material science principles. And that's also something I want to emphasize, that chemistry aspect of the materials design, composition design, doping, and all those things are very important to help us stabilize the material. But there's another factor which is really at the heart of material science, which will be the materials microstructural control. And that can give us another leverage in further fine-tune the materials, and then potentially to get very low temperature manufacturing as well. So I strongly believe that our university research will play an important role in the technology innovation and workforce development. And throughout my presentation, I mentioned the name Fermi Energy over and over again. There's a conflict of interest here I need to emphasize. I'm a co-founder and shareholder of Fermi Energy. The presentation is contributed by all these amazing individuals and collaborators and students and postdocs now and in the past. And then the National User Facility sponsors of this presentation of the work presented here, Department of Energy, NSF, and my previous employer, Virginia Tech.